Excellent, fantastic, great. Welcome, friends. Welcome everybody to this year's Coming Up to Speed summer course. My name is Pablo Giuliani. For good or bad, I'm going to be your mentor for the following couple of months. I hope that it's going to be more good than bad. I'm actually very excited. Hello, welcome. I am an academic staff working at EFRIP, and I'm in charge of helping all the grad students there, and to some in some extensions to the grad students of physics and astronomy. My main job is to make sure that everybody is thriving instead of struggling. And this is part of a big initiative that we're trying to take to make the education process better. So part of those things that I do was to come up with this course. This is my TA, Josh, and I am going to mispronounce your last name. Josh, how should I pronounce your name? It's Josh. But the last name? This is Josh, a very friendly fellow, and he's going to join us through this entire adventure. So I am very bad with names. I already have told a couple of friends here that I already remember Daniel Cooper. Oh, fantastic. So these are Daniel and Cooper. These are incoming grad students. I would like to ask from left to right on the room, can you introduce yourself?
Hi, I'm Danielle. Third? I don't know. I've lost count. Probably third year casting.
Very good. Thank you, Danielle.
I'm Allison. I'm incoming Astro grad.
Fantastic, Allison. Thank you.
I'm Grace. I'm second year. I just rising.
Excellent.
Alex, also an incoming second year, rising second year.
Fantastic. People in Zoom, any one of you wants to unmute yourself and introduce yourself? If your audio doesn't work or you're shy, that's okay as well. But this is your opportunity if you want to say your name.
I'm Gabby. I'm an incoming grad student next year.
Oh, I see what is happening. That's why it was my problem with this. Give me on the audio. Give me just 1 second. You're in my headphones. That makes sense. Okay, can you give that a try again?
Yeah, my name is Gabby, and I'm an incoming grad student this fall.
Fantastic. Very nice to meet you, Gabby. Now I can hear you well. Tessa, do you want to give it a try again?
Sure. Can you hear me?
Now I can hear you.
Awesome. All right. I'm Tessa. I'm an incoming astrophys grad student.
Fantastic. Very nice to meet you all. Okay, I think that's everybody that I have in here. Welcome all. So I will try my best to memorize your names. It might take the whole summer, might take less. We'll see. So the first things, I'm going to spend the next 10 minutes going over the structure of the course, why we are taking this course, what you can expect of me, what I can expect of you. And the most important thing that I expect from everyone here is that you behave very nicely. There's many documents out there, some religious, some institutional, that tells you, be nice to others, don't do to others what you will not want people to do to you. And I will expect that everybody behaves in that way. If not, we're going to have trouble because I will have to drag you out of the room. So here, if you have never seen them, here are 2 code of conduct documents that explain in detail what that means. And if at some point you're confused about that, or you feel that somebody around you is not behaving in that way, please let me know. This is very important to address. Okay, the second thing that I want to say is a big thanks to the team of people that have helped to put all this together. We have been running this program since 2023, so it has successfully run for 2 years, and this is the 3rd year. And I hope that as we go around, we improve it even further. Now, I want you to think with me why we have this course. What is the objective of this course? And yesterday I was playing with ChatGPT, trying to create a good way of explaining what I have in my head on why. And I think we came up with very pretty pictures. I want you to look at these pictures, and beyond admiring the artistic effort that ChatGPT made, think about it in terms of the adventures that you have had in your undergrad years, for those of you that are joining us right now, and in your grad school years, for those of you that are already in grad school. this is a summary of thinking or a way of representing all those adventures that you went through. So I have a picture of somebody in the moon with a tiny space station. I have someone drifting a boat in the Amazon rainforest. I have a cabin in a very snowy mountain, and I have a tent in the middle of the tepuis in Latin America. So this is what you have been doing up to now so far. And this is how I think grad school looks like. You're embarking this journey in this boat, and you're sailing towards this land of things that you have not explored, or there are many parts of it that you have not seen yet. And even though you have taken all of the adventures that I mentioned before, each one of you did a subset of that. And it might be that even though you have explored a lot of parts of the earth, you have never had to tie a knot to a boat. You have never had to deal with rust in the materials that are under your feet, etc., etc. So I want you to, as we go through this, and as you go in your education, I want you to think, you're all adventurers, you're all scientists, you were accepted into this program, that already happened, you belong here. If there are parts of it that you do not master yet, that's fine. That doesn't mean that you're not cut for the job. It just means that we have to focus on those parts, and you have to learn how to do this specific type of adventure that we're going to be sailing towards. Does that make sense? I want to encourage everybody also to interrupt me and ask questions. I have specific points during the class in where I'm going to interrupt myself, and we're going to take a break, because if I monologue for an hour and a half, I'm going to kill us all to death of boredness. But at any point, if you feel the urge of saying something or asking a question, please do so. So take this in mind. We're going to talk about imposter syndrome later, but that's something that happens a lot, where you have done amazing things in one type of the adventure book, and you find challenges in other parts, and that might make you feel bad. It certainly made me feel bad when I was starting grad school. There's going to be a bunch of resources for you beyond coming to the lectures. This is a folder link in where I'm going to put a bunch of materials and things. This is going to be for the 2025 one. I will send a link to all of your emails at some point. I think I have all of them, but you can also take a picture, and here's the QR code. We have a forum that me and my friend Kyle Godby put together, and we're going to use the forum to communicate things including, hey friends, I had to go to emergency to the dentist. My mom was right. I should have flushed my teeth, and now I'm in emergency and I cannot teach next week. I will communicate those things through the forum. But also the forum is full of resources already. We have some professors in particular that have gotten very excited about it and have filled it with a bunch of materials and questions and answers, Jay Deep, the biggest among them. So I encourage you to check the forum and to make an introduction so that I know where you're coming from and what are your thoughts. We have a YouTube channel in where I have part of the lectures that I gave last year, but also some introductory courses to Python and coding. This is going to be very useful. If you have never seen coding, like I never saw coding when I entered grad school, we guide you step by step on these videos, including on the use of AI, in this case ChatGPT, as a tool, not as something that will replace you. Oh, this is very important. I have to give a disclaimer and ask all of you. I am recording that. That is that phone over there. Hi, people that are looking at us in the future. And I intend to record the entirety of these lectures such that A, we can put them in YouTube for everybody in the world to enjoy if it's useful for them. B, for you to enjoy these things 3 months in advance when you're in quantum mechanics and you're like, oh, shoot, I should have paid attention. What did Pablo say about Ketbras? So you can watch these things again. And 3, and I think probably this is the most important because some of your colleagues are still not physically here and they cannot join us through Zoom. Maybe they're in Thailand, and in Thailand we have many hours difference, and this is not a very good time. So all of this is to say, I am recording this, but I can always edit things out, especially since, and here I have a picture of last course, that friend got immortalized with me while we were playing with normal modes. If you are shy and you don't want to be featured in camera, or you want to ask a question that you don't want it to be put in the future into posterity, you tell me, and this is very easy to edit. Everybody's clear with that? And if you're even too shy to tell me directly now that you don't want to be featured in camera, there is my email. You can send me an email and say, Pablo, just please don't put me. And nobody else has to know about that. Make sense? Cool. Excellent. Okay, we have a GitHub repository as well, in where you will find a lot of resources, including what are called Jupyter notebooks. That is a mixture between code and text. So it's kind of the modern way of having textbooks. So you can read about it. That's the first one is on derivatives and integrals. It was made by a lot of people, mainly Josh Wiley last year. It guides you through the process on thinking about these things. But the nice part about having this in code is that then you can make this type of plots and animations. This is an animation that I made for two-body scattering in classical mechanics, so you can get a more intuitive pictures of what all this means. So check it out. That is something that will join you in the rest of the course. The meeting structure. We're going to be meeting Mondays and Wednesdays, 1:30 to 3 p.m. From now until August. I don't know exactly when in August, whenever we get bored. There might be a week in where I should take vacation and go somewhere. I will let you know when that happens and we will reschedule. All the meetings are going to be in this room except for 2 or 3 that this room is occupied. And I think the first one is 9th of June or something. When that happens, I will put a post-it note on where we are meeting. It's in another room nearby. I just don't remember the name. The objective of this is to empower you with your science/adventure identity, that you feel, heck yeah, of course I can scale mountains and explore waterfalls and then go in a journey to see new islands. I want to give you pathways to understanding. I want to help you find ways in where you're sitting at night, you have a homework for quantum mechanics and you're completely lost and you have no idea what there is that you need to do. How can you unstuck yourself? How can you start thinking of different ways of visualizing, not exactly what is happening, not in all detail, but at least to have an intuitive vision of what the problem is asking so that you can progress. And of course, the important part is we need to cover some critical concepts like eigenvalues and eigenvectors that will be crucial for your courses to come. This is usually the main structure that I will have in the class. A part of me monologuing, I will have 1 or 2 in-class activities that I will encourage you to form friends and groups, and you try to tackle it in groups of 2, 3, 4, half the class. I don't mind. When we do that, some people, what I'm going to do is I'm going to mute my microphone, and Josh is going to go to the other room, and you're going to be able to participate in the Zoom discussion. So that will be 5 minutes of class activity. You get to solve that with Josh, and then you come back, and then we can all compare answers and talk about it. I'm going to give you playgrounds. I call them playgrounds instead of calling them homeworks, because this course is not graded. You don't win anything by doing any of the things that I say, and I'm not going to grade you either because I'm extremely lazy. So I want to think of this as playgrounds. I'm going to offer you things that you can play with. And if you want, you can play with them. You can post it in the forum. You can ask help of people, me included. And it can help as a living resource that will help other people in the future. And I will talk about the homeworks in a second a bit more. I will have a lot of analogies and connecting concepts. So it will definitely feel very different from previous classes that you have had and the recordings that I already specified. So I'm starting Duolingo. I'm learning Polish. And one of the very nice things that I have found about Duolingo is the fact that it gives you this reward system in where if you keep a consistent streak on your lessons every day, you practice every day, it gives you this tiny count in where you feel that you're progressing in a game, which sounds so silly. If you're really trying to learn a language, it should be enough that you feel that you're learning the language. That should be reward enough. I am silly, and I really like to have the thingy that tells me that I have been nonstop doing this for 23 days so far. So I'm going to give you something similar. Whenever I send you homeworks or playgrounds, I'm going to collect after each class by word of mouth. If you were able to play with the thing, doesn't mean that you solve it, but you play with it. And Josh and I are going to cover a list. And at the end of this course, I'm going to give you something like this. I'm still designing a better version of this collectible. This is the first time that I'm doing this to see if it works, because last year nobody paid attention to me and 2 people did the first 2 homeworks and that was it. So you will be able to get these tokens in where the different marbles are. How many homeworks of this thing have you tried and attempt? Imagine in the future sitting in your office with this thing next to you. It will be fantastic. Who will not want to have this to accompany you for the rest of your PhD? And more seriously talking, think that all of those little efforts that you put are going to be part of the cargo that you're going to take with you to explore the islands in grad school. It will pay off. So, think about it and do it. This is a menu for what we're going to do in the next 2 months. The first 2-3 weeks, we're going to cover math and coding, roughly 5-6 lectures, where I'm going to be talking about calculus and linear algebra and differential equations and all that good stuff. I will also cover some basics of coding. You have the videos, but maybe at some point I will bring an expert in class to have a session in where you bring your laptops and we play with Codespaces for a bit. Codespaces is a GitHub thing that you can use to run Python in the cloud, so you don't have to install anything in your computer. In math, we're going to cover derivatives and integrals, Taylor series, vector calculus, differential equations, linear algebra, which is extremely important because quantum mechanics is just linear algebra 95% of the time. We're going to talk about complex numbers and Fourier transforms. In coding, the basic Python and how to use Codespaces, how to use AI, and how to read documentations of codes and so forth. So that will happen during the first 2-3 weeks. And the way that I will do it is both Mondays and Wednesdays will be focused on this. When we switch after that to the 6 to 8 weeks of classical and quantum mechanics, Mondays are going to be classical mechanics and Wednesdays are going to be quantum mechanics. This way, if you're already an expert in quantum mechanics and you only are here because you really want to get better at Lagrangians and Hamiltonians in classical mechanics, you can only come on Mondays and don't have to listen to me on Wednesdays. That's the idea. I strongly recommend that you come both of the time. I like you all already, so I think we're going to have a blast, but that's the purpose of that. And here the menu, and they're also specified in the forum. I'm not going to read it through. Any questions so far? Some people, any questions or comments? Fair enough. So with that, we're going to start the first lecture. Oh, by the way, I have chocolates in there. You're free to grab chocolates. Some people, I own you the chocolates. I will give them to you when you come. Okay. Can you see? Can you all see? Does this make sense? All right, excellent. So let's start. We have already covered this part. Let's talk about calculus. So now I'm going to be talking with many open questions. What is calculus? I need brave souls, brave volunteers to tell me what is in your mind. Why anybody cares? What is all this about? And since this is important, if you don't mind, while you chat, make sure to have this around. You don't have to put it close, just have it around. Aha. So what is calculus for you, Daniel?
I don't know. It's at least derivatives are doing limits without most of the work.
So I hear the word
limits.
derivatives, I hear the word limit, makes sense.
Mhm.
Why anyone will care about limits and derivatives?
It's you take the derivative, it's velocity, second derivative, acceleration, it's motion.
Okay, I'm hearing dynamics, hearing that something close to we probably can describe the motion of objects using derivatives at some point. Someone else? Alex?
It has to do with
Take it
rate.
a bit farther away.
Okay,
There you
it has to do with rates of change.
Huh?
So how to deal with those mathematically, and then how to kind of go back the other way, like with acceleration and velocity.
Rates of change. I'm going to put in here dynamics. You also said limits. Okay, what else? Calculus. Beyond derivatives, what else is in calculus?
Like behavior.
Grace?
Yeah.
Oh, I'm amazing. Wow. Go ahead.
Like behaviors of functions.
Yeah, yeah. Behaviors. Nobody has talked about integrals yet. Some people, now it's your turn to be brave. Any of you want to comment what is the integrals part of calculus? You can also type in the chat and Josh will be your voice. I think, or some people are shy.
Like being able to find areas through integration.
Ah, fantastic. Thank you. Areas. Let me put that in here. Thank you, Daniel. So I'm going to put in here areas. I want you to look at what I have on the screen right now. Is it really this? Do you go, do people annoy you to go for an entire set of semesters in undergrad just so that you can find areas under curves, just so that you can write accelerations? Seems a bit anticlimactic. Let's put a pin on that thought. I'm going to ask you a different question right now. I want you, this is easier. I want you to list some inventions that you know humankind has made before the 17th century. I'm going to start. Fire. Kind of not an invention, but more or less. Somebody else. And you still need this thing. So I'm going to leave this. I think if we put it here, it should capture the room. Tell me.
The wheel.
The wheel. That's another one. Yes, very good. So I have two. What else? I'm counting, by the way. I'm keeping track.
Printing press.
Printing press. That is definitely before the 17th century. Thank you. What else? I'm going to chime in another. Boats. We invented boats.
Paper.
April?
Paper.
Paper. Yes, that's true. What else? Some folks, anybody has any idea of any other inventions before the 17th century? Yeah. Not very good roads, but yes, roads.
Roman road is still here.
Very good roads then. That is very true. Aqueducts. That is also from more or less than period. Okay. Sorry? Catapults. That's very true. And without using calculus, imagine trying to calculate where the rock was going to land. So I have 7. We're able to list 7 is a very nice number. It's the number of holes we have on the face. So I'm going to stop now. How about the number? How about a list of inventions after the 17th century? I'm going to start airplanes, computers, electricity, satellites, rockets, pretty scary weapons, the internet, cars, trains, the steam machine. I'm already at 10. Anybody else wants to add anything that I'm missing? Refrigerators, air conditioning is so important. My goodness. Why? What is the difference? What happened after the 17th century? Calculus. After the 17th century, we had calculus. So it has to be something else that is not just the areas under the curve or describing functions, which, yes, those things are important. But there is something fundamental that as a civilization, once we discover calculus, things shift to a different gear. And we're going to talk about that. So right now, I am going to transition to a break. I want you to think about these things. It is 1:56. We're going to be back here at 2. I encourage you to go to the restroom if you have to. Some people do the same. I'm going to stop sharing my screen, and then we're going to come back and we're going to start talking about that. Okay, friends, we're ready to come back. So, we talk about inventions. I'm going to put it in here. Inventions and technology. There is definitely something more to calculus than what is usually presented in some courses. So what we're going to do now, we're going to dive deeper into derivatives and then integrals. This is not a formal course, so I'm not going to be proving any theorems. I want to give you intuition on how to look at these subjects. And we're going to solve a couple of problems. So let's start with derivatives. The idea behind derivatives, if you were to stripe it down to mathematically what this means, is exactly as one of you said, is trying to track rates of change. I have some functional relationship between a function y that depends on a variable x. And by the way, yeah, no, that's good. Alex, sorry, can you check that that thing is still green? The microphone has a green light?
It has a green light.
Okay, perfect. Leave it there. All of you just be aware that that thing is recording me so that I can hear, people in Zoom can hear from. Anyways, I have a function y as a function of x. And the idea of a derivative is asking yourself the question, if I make a zoom, I look at this locally, and we will talk about this later when we talk about Taylor series, but if I try to like really zoom in and I ask myself for a small change in x, that is my control variable, how much is my response variable changing? And it's a ratio between those two things that ends up defining a derivative. The reason why this ends up being useful is because there is a mathematical way of calculating a derivative for most of the functions that we're interested in. For example, if you're talking about a function that looks like x squared, you have probably all seen and are familiar on how to mechanically take a derivative. The derivative of this object is going to be 2x, meaning that if you give me a particular x value, I don't know, let's say the number 3, the rate of change of that function at that location is going to be 6. For every small movement that you do in x, you're going to get 6 times that increase in y. That's how you mechanically will take derivatives. Once we have that, why is this useful? I can use it to, for example, make tangent curves, the same way as people can use integrals to make areas under the curve. I can use derivative to find the straight line that better approximates my function at that point. And why is that useful? So I'm going to argue that there's many ways in where you can slice this cake, but the usual 2 ways that I really like to slice it is optimization and differential equations. To me, these are 2 of the main reasons why derivatives are going to be useful. Why optimization? Let's think about that one. I came up with this problem, trying to motivate it in a more physical way. Imagine that you have a river. This is my river, and you're trying to build a fence for, I don't know, you have some raccoons or some horses that you're taking care of. You're trying to make a rectangular fence to contain the horses. And somebody told you you need an area of 100 meters square or your horses are going to be very unhappy. And the variables that you can play with these, you're going to have a variable, let's say x, which is the side of the pen, same here. And then you have a variable y, which we're going to say is the length that you have on the parallel direction to the river. And you're asking yourself the question, what is a good value that I can choose of these 2 variables to build a pen that has a fixed area that is 100 meters square, but with the smallest amount of perimeter? You can all see, if I were to make a very thin rectangle out of this thing, I will get my 100 square meter area. It will be very inefficient in terms of perimeter. Yeah, does that make sense? The rules of the game, what I'm trying to play in here. All right, how do we solve this problem? Like, literally, you could be sitting somewhere, taking a nap, and then a farmer comes and asks you, I hear that you're a physicist or a scientist. You need to help me with this thing, and now you have to figure this out. So the way that you can do this is you say, well, let's make the function L, which is the length, as a function of x and y. How much wire or fence do I need to pay for? Anybody wants to tell me how much this is going to be?
2x.
Ah, fantastic. Very good. Now I have 2 variables and I want to optimize. Do I really have 2 variables? Not really, because I have a constraint. I say that the area of these 2 things, which is going to be equal to x times y, this has to be equal to 100. Yeah? So that means that y is equal to 100 over x. So long as I make y equals to this, I will always respect the area that I need. So this function, I can actually write it as a function of x alone. And then I get 2x plus 100 over x. Everybody's with me? And now I want to do what? What is the engineering problem that I'm after? What I'm trying to find? the minimum value of L as a function of who? How do we solve it? Sorry? Probably taking derivative, given that I'm talking about derivatives. Derivatives is the answer, but why derivatives? What is the reasoning behind that? Very good. Yeah. So if you had the patience to make a plot of this curve as a function of x, you will find something that looks like this. For very big values of x, you have something very inefficient because your rectangle is very stretched. For very small values of x, the same thing, but because of it's in the other direction, it's because of the response of y. There is an optimal location here, which is, no, that's x2. I don't want to. Here, this is what I'm after. Now, this will cause you to sit down and look at every value of x that you can if you didn't know about derivatives, and then you have to select it. But thankfully, we don't have to think in that way. The reasoning is, remember that we were talking about rates of change. A property that a minimum value of the function will have is that once you're in the minimum, for most functions that don't look too pathological, if you change the input a little bit, the output will not change that much. And you can convince yourself of that by looking at the figure. So this means if you're able to find the place in where this curve has a derivative that is horizontal, meaning the rate of change of y of the response function L with respect to x is 0, then you will have found your answer to your problem. In one dimension, for this simple example, and with a computer, you really don't need derivatives. You can just plot it and select, here it is, and that's it. If you have a function of 7 dimensions, it's kind of complicated to visualize that, so you rely on the generalization of derivatives to find the optimal. Does that make sense? And in this case, so if you were to take the derivative, you will have dl at dx is equal to 2 plus 100 over x squared with a minus, if I did this correctly, and you want this to be equal to 0. So from here, you can figure out that x is equal to the square root of 200. And that's it. You solve your problem using calculus. Magic. Make sense? Did I do it right? Sorry? Yes. Very good. That was to see if you were paying attention. You got it. Good job. Makes sense so far? Good. Let's play again so that you can think of how this feels in multiple dimensions, as I was saying. I need a volunteer. Cooper, come to the center of the room. So I need to remember where you were. Are you okay being recorded? Yes. Is everybody else here being recorded okay with you? All right. So I'm going to set this one here. Oh. All right. So I have hidden a present in the room, like for real. Okay. It's for you to find. And we're going to start playing a game of cold and hot. Have you ever played that game? Yeah, you know how it's played? So because I really want to drive the point of calculus, here you go. I want you to try not to poke anybody in the eye. I want you to treat the tip of that as where you're evaluating your function, because I'm going to be giving you instructions in X, Y, and Z. So depending on where you put it, your person might be close to the threshold, but maybe the tip of that is not. Make sense? Okay, so start searching. I'm going to tell you hot or cold. No, buddy, you're very cold. Oh, it's getting hotter. It's getting hotter. Try really not to poke anybody. It's getting a bit hotter. Yes, I can definitely start feeling things are getting toasty. No, you're going, no. Yeah, I think things are getting a bit colder. And more hot. Oh, it's getting hotter. No, now it's getting a bit colder. Oh, it's getting closer. He seems to be closer to Josh now. Oh, no, it's getting very cold, but he needs to go around the room. That makes sense. It's getting colder. It's getting colder. It was better. No, even colder. Oh my goodness, freezing. Better, way better. That is the direction that I like. Maybe yes. So now we have to go to the other row. This is, by the way, this is what a computer is doing when you're doing an optimization numeric. It's getting better or hotter, very cold. Oh my goodness, it's burning. We have found the present. So what do you get, buddy?
For one, ice cream.
Excellent. You got an ice cream from the dairy store. So I actually wanted to get you like an actual ice cream thingy, but the dairy store is closed today. I will give it to you tomorrow or Wednesday. Don't forget about it. Okay, let me put this one here. So whenever you're doing, and it's a real ice cream, like I'm not lying. Good job. So whenever you have a numerical optimization code that has a function that can be a function of one variable or can be a function of many variables, in here I took the derivative by hand, but computer-wise, what will happen is you will have a cost function, let's say the length. By the way, I just realized some people that you were not able to see what was happening. I'm sorry. Next time I will move I have two cameras now. I didn't have that before, so I forgot. Anyways, he just basically found the secret ice cream in the room. So computers, back to optimization. Numerically, how is this working? You have this guess in where you start, and you're going to start playing the game, in this case in one dimension, so it's very boring, of do I move left or do I move right? The computer is like Cooper, and is thinking whether to move the stick to the left or to the right. The computer moves the stick a bit to the left, and the cost function says like, ugh! The computer moves the stick a bit to the right. Oh, this is nice. I like this. Things are getting better in terms of temperature. So the program starts walking downhill until eventually maybe it makes a jump here. And when it moves the stick to the right, the cost function tells you, nope. Move to the left, things get better, and eventually you find the minima. That's one of the many reasons why calculus is extremely important. You're able to optimize things. The second reason has to do with differential equations, and we will talk about them in more details later, but I want to give you the idea. As humans, whenever we're trying to model things in nature, we are not very good at just coming up with how things should move. And to give you the idea of saying, I don't know, I have the solar system and I'm trying to trace how the planets move. If you ever read how, who was it, Kepler, using the data from Tycho Brahe, I am butchering their names, but if you read how many years it took for him to figure out, I think these are ellipses that are moving around the sun. It's a gigantic amount of time of just trying to come up with the solution. I'm going to name the solution as, so let me see in here, this was optimization, this is differential equations. Some of you were talking about dynamics, and if I were to say to you, oh yes, I'm trying to figuring out that if I have the sun, the orbits of the planets are ellipses around the sun. Oh, that's a square, no, that's an ellipse. Can you make an ellipse? Nope. There you go. If I'm trying to figure this law out and say that planets move in ellipses around the sun, it's very complicated to just come up with, this is a solution. This is hard to do. But what is not so hard to do is to think, not of the entire trajectory, but instead, think of this planet has some velocity. It feels a force that goes towards the sun. And maybe it feels a force of some of the other planets around. Writing locally what is happening to this planet is very easy to do. To say what are the forces that are acting on this, what is the current local speed, the current acceleration, the current position, and writing that out is what ends up being a differential equation. We will tackle that in classical mechanics, but eventually you basically write an equation that says the second derivative of the position with respect to time is proportional to the forces that act on the system. And this is a differential equation on the variables that you're after, which is the position of the planet. This is easy to write. Then it's your problem, buddy. You have to find a solution to this horrible thing that you just wrote, but you can write it. That is something that is usually very hard to do if you're trying to just come up with the solution itself. I'm going to argue on the derivative side that these are the two main reasons why we will be interested in studying calculus. Does that make sense? Does this help? If in the future you're walking down the hallways of this beautiful campus and a professor asks you, wait a minute, so why do you study calculus? At least on the derivative part, do you feel that you can say a different answer than just tangents and behaviors of curves? Yeah? Good. Excellent. That makes me very happy. So we still have 45 more minutes in where I have to talk about stuff. So what we're going to do now we're going to do the first in-class activity. I am going to share my screen. So, Josh, this will be the moment in where you go, but let me explain the activity first. I'm going to ask all of you to form groups. Some people, you're just going to be one single group. Form groups, and you're going to tackle this chart that I have in here. Let's say, I don't know, 10 minutes, between 5 and 10 minutes. Let's say 10 minutes. You have to, oh, this is really hard to see. You have to talk together. That is a very important part. Do it in teams and come up with the answers to this chart. You have the position, the velocity, and the acceleration of an object. The velocity is a derivative with respect to time. The acceleration is a second derivative with respect to time. So your job is to figure out this puzzle. Who should I put? Where should be E, the function E? Where should it go? The function F. And then we're going to compare together. So I'm going to give you 7 minutes because I do have to talk about integrals. Go for it. Josh, go to the other room and talk with the Zoom people. I'm going to mute here. So this will still be available, but I'm going to mute everything. And I'll see you in 7 minutes. Let's say 2:25. You think this worked well? Yeah. Excellent. Very good. Okay. So we have in total 3 groups. So I would love to hear input from the 3 groups. Do we want to start with people in here? I'm going to start in this way. Tell me, where do you think we should put some of these curves? And let's turn this on. Let's put it here. By the way, some people, can you confirm to me that when the room talks, can you talk?
Yes.
Can you hear the room?
Yes.
Excellent. Oh, very good. Oh, wow. You all should be very happy. I have optimized this over the years. The first year was a mess in comparison. Okay, so I'm going to start with this group. Tell me some of the curves. What do you think?
So we were looking at chart E.
Uh-huh.
Decided that because it's just a straight line, it's
Yep.
constant, that would make sense for the velocity graph corresponding with chart A.
I think so.
Because that looks like it's a constantly increasing slope rather than just a constant slope.
So we're having this discussion. If anyone is not following, please interrupt and ask questions. Because especially some people, I can see all the happy faces in here doing this, saying yes, yes, but I cannot see you. So please interrupt if yes. So I think that makes sense. So who should be the acceleration for that case?
We were looking around and thought that either G or J would be a good option because they're both constant.
Yep, G or J,
Negative.
but which one?
G was negative and J was positive, and this is decreasing.
Fantastic. So G is negative, J is positive. I look at the speed, and it says that the speed is increasing as a function of time, so the acceleration should be positive. So I'm going to put a J here. Excellent. Good job. Thank you. The other in-person team, tell me, what do you think?
We have F for the position of the second column.
Okay.
Because it looks like B starts out positive and then has a constant negative slope that crosses 0 and goes negative. So F should make sense since it hits that maximum like towards the beginning. I can't remember exactly.
Yep.
Two or four maybe.
Around.
And then for the acceleration, G makes sense for the same reasoning except negative.
Exactly. Yep. Very good. So yes, ways of reading this. In this part of time, the speed of my particle is positive. So my particle is advancing in the positive direction. That is exactly what is happening here. It's slowing down, but it's still going up all this time. Eventually, doesn't go up anymore, has derivative 0. The derivative 0 of a position means that your velocity, instantaneous velocity at that location is 0, which is exactly what happens here when it crosses 0. And then speed becomes negative, ever increasing more negative, but negative. And that is what we see from now on, that the particle is tracing back. Does that make sense? This looks like a parabola. The speed looks like a straight line. Probably the acceleration is constant, and it has to be constant equal to the, with the appropriate sign. So you put in here G, which I love it. Makes sense. I'm very happy. Excellent. Soon, people. Any of you wants to mute and tell me the next ones?
So we said that K was for the position since it's initially
Mhm.
increasing and then it's constant. And then there's a negative velocity. And then L would go for the acceleration.
For the
because
acceleration or the, okay, sorry, K for the velocity?
oh, sorry, I was doing the last one.
That's okay. Okay, so are you in this column or in this column?
Sorry, I skipped to the second column on the
Perfect,
right.
that's okay. Let's do the second column. So for this one, can you repeat K should be where?
For the position.
I think I agree. Let's see. So in here, I have an increasing speed. So an increasing speed means that my position should look like a parabola. This looks like this because the integral of a straight line is going to be a parabola, or the derivative of a parabola is going to be a straight line. So yeah, that makes sense. And then speed kind of gets constant during this period. I see that in this period in here, in where the position as a function of time becomes a straight line, that means that the speed is going to be constant. So I think I agree with you. Anybody else has any comments with respect to that? B and K? Okay, so what about the acceleration? I want to memorize the names of some people as well. Was this Gabby or Tessa?
Oh, this is me, Gabby.
Gabby. So tell me about the acceleration, Gabby. What do you think?
It's positive. I thought it was L for acceleration. I'm pretty sure that's what we said. So it's initially positive and constant, and then it drops down to 0.
What do the rest of people think? For should this be L?
It's not slowly drop, it's just
Well, I don't know.
there's no acceleration happening. It's just switching speeds instantaneously.
You know what? That's true.
Yeah.
Yep, you're right. This is L, and this is L, and it's wrong. So funny enough, I already ran this by the 2024 cohort. I don't remember. Maybe. So you're absolutely right. That is correct. If we skip like 3 lectures and I put a bunch of delta functions in here, which are kicks that are infinitely strong but lost an infinitesimal amount of time. So yeah, that was a tricky one. Good job, Gabby. Very good. I need to check with Josh what the heck we were expecting to do here, because I don't think we were expecting you all to think in terms of delta functions. But that's correct. Good job. Okay. So I have half an hour to talk about integrals. Yes. Then H and I, is that an I? Should be for the other two. You can figure that one out. I want to start talking about integrals, or we'll not have enough time to do so. Okay, so now excellent. In only an hour, we were able to cover all of the derivatives. To think that your math courses needed an entire trimester or semester for that. Let's talk about integrals now. So as I mentioned, integrals, same as derivatives, integrals can be used for things like finding the slope of a function, finding the area under the curve of a function. But I want to build an example of something that has a more engineering or scientific flavor than just finding the area under the curve. Believe me, I do a lot of math, and I don't just go around trying to find the area under curves half of my time. There is something else that we can do with this. So the problem that I invite you to think, we're going to skip many lessons because I will never talk about in detail electricity and magnetism in here, but it's one of the best examples that I can make to explain why this will be useful. I want you to think of Coulomb's law, that probably you have seen it in your undergrad or in one form or another. Coulomb's law tells you if you have a charge Q and you, my friend, are interested in the electric potential at a location R, and you have a system of reference that I'm putting in here, your charge is at location R prime. And actually, I'm messing this up. Your thing is at location R prime. And I'm trying to find the potential at a location R from my system of reference. Anybody has any idea? This will be R minus R prime vector. How can I express the electric potential or the electric field, whichever you prefer, at my location R? Any volunteers can tell me the answer to this question? Some folks. Any idea? You remember? If you don't, that's okay, because you don't get to see ENM until your second year, your second semester, so that's okay. Okay, so you remember?
I'm gonna take a stab at it.
Uh-huh,
The
go.
potential specifically, or like Coulomb's law?
It's a potential from Coulomb's law.
Okay, it's 4 pi.
There is a 4 pi. Don't worry about constants. That
then,
doesn't
like,
matter.
The integral.
No integrals because it's a single point charge. It's a point charge. K cube. Perfect. So let's unwrap that. There is a K that is just a bunch of numbers. 1 over 4 pi epsilon 0. I really don't care. I'm going to erase the number. Don't think about the number. Some number. But it's proportional to the charge Q that I'm going to put in blue. Makes sense. Twice the charge, I will have twice the electric potential or the electric field. And it's divided by the distance. The distance of what? Distance of whatever you are trying to calculate the potential and whatever the source for that potential is. So in here, I'm going to put the difference between R minus R prime. And if you want to make this not a wiggly tururu, but an equal, you just put K, which is the 1 over 4 pi epsilon 0. Makes sense. People recognize this. You have worked with this in the past, yes? Now, this is an easy problem to solve. What if, instead of this problem, I give you, come here to the land of complications, and I don't have a charge Q. I have a potato. I go to Myers, I buy a potato, has the shape of a potato, a very ugly potato. I electrically charge it. I don't know how I did that, but I do that. And now I ask you, same question, what is the electric potential at this location? What do? I can no longer write this because I don't have a location R prime, but the question still remains. What is this? Any ideas?
Potato into infinitesimal chunks. Yeah.
So somebody's talking about cutting the potato, and I'm getting hungry because yesterday I actually cut potatoes and made potatoes with steak. Yes, I like that idea. So here's what we're going to do. We're going to slice this thing up into many tiny cubes, as if we were going to cut the potato. And I'm going to focus on one of those cubes. This tiny cube right here. Now that I'm talking about a tiny cube, I can talk about the position of this tiny cube. I can talk about the tiny charge of this tiny cube. I'm going to call that dq. Why d? Infinitesimal. I'm going to borrow the same language from derivatives. It's a small amount of q. And I can talk about the distance between that tiny cube and the location in where I'm trying to evaluate this thing. That is going to be R minus R prime. Yep. Everybody with me? Excellent. Fantastic. So then, instead of asking the question, what is the electric potential in there, I'm going to pretend that my question was, what is the tiny potential that that tiny charge Q creates there? Can somebody tell me what is the tiny potential that my tiny charge Q creates there? No, what do you mean integral? Now, We have no potato. Potatoes don't exist anymore. It's just about a tiny piece of potato. How much?
8 dq over r.
1 dq over r. Who's r? Right? It's the distance between whatever I am evaluating and what is creating this thing. This thing now has a name. It's this cube. So it is this distance. R minus r prime. Right? Make sense? Exactly the same thing we had before. Nothing has changed. It's just that I'm talking about the tiny cube that is in a different position than the other cube was. So, well, if I want the total potential, what I have to do is to sum. This is a symbol for summing over all the tiny dq's. I want you to think whenever you see the integral symbol, this is an S for summing. You're going to add all the contribution of all the tiny dq's together, and that is going to give you the final electric field or electric potential that the potato creates in there. We're not going to work out the math. The details don't matter, but this is what I want you to have in your mind whenever somebody asks you, what are integrals powerful for? Is something that allows you to add the infinite contributions, to add all the contributions of an infinite amount of infinitely small objects together to get a finite macroscopic effect. That is huge. That is amazing. That is what allows you to design things. For example, make the blueprint for a bridge and try to distribute the tension and try to integrate how much mass I'm going to have to support with these things. That is the type of power that you get out of this. Now, this sounds awesome. How do I do this? Because if you were to tell me, well, Pablo, you literally have to cut the potato into infinitely small pieces and add them all together, it's like, that sounds nice, but I don't know how to do that. That is not useful. When is this useful? When you have access to the fundamental theorem of calculus. So except for Cooper, because he has already answered a couple of my questions correctly, anybody has any idea what this theorem is for in this context? What is the powerfulness of this theorem? Why what I have written in here up to this point is but a dream of spring and nothing very concrete and useful that I can do anything about. I know you like areas, so let's say that the equivalent of solving the potato problem has to do with finding the area under a parabola between 0 and 1. And that's what makes integrals. You can think that this is, I grab my tiny area and I split it into tiny rectangles and I'm summing over all the rectangle. That's what it means if this is f of x. I'm interested in the integral of f of x dx. This is tiny rectangle area. So same nonsense. I'm saying very pretty words. I would love to be able to sum all of these things together. How? Where does the fundamental theorem of calculus enter? So Daniel says, somehow I can access this information by evaluating my function at the end and the function on the both ends. And that is half correct. That is not completely correct. We're getting there, though. What is this? What is the fundamental theorem of calculus? It has a fundamental on its name. It must be very important. Any ideas? And I am teaching this class. If I expected you to all to know this already, I will be wasting my time. It's okay that you do not know, but I just want to hear if there is anything in your head that relates to this. And if not, that's okay. Thank you. I'm very glad. This is a powerfulness that tells you you have derivatives living here. What are derivatives? We already discussed. Rates of change, infinitesimal, blah, 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 optimization, differential equations. And you have integrals. And the fundamental theorem of calculus is a bridge between these two things. It's something that tells you these two things are two sides of the same coin. Actually, they're anti-sides of the same coin. There are anti-operations. Meaning, if you want to find how much is this integral, this area under the curve, you need to find yourself a function g. And you evaluate that function g. Let's say that this was a and this is b. You evaluate g in b minus g on a. And that will give you your area. And who's g? G is a function such that the derivative of f with respect to x is g. Simple as that.
Hello, friends. So, editing last day's video on Math 1, I realized that I had a mistake. And I'm going to correct the mistake right now, and then we're going to continue with the class. So, with the video you're watching. In the class, I said that the function g, you could obtain it by taking a derivative of f. We usually call this the integrand, the thing that you're integrating. And in this example, I was taking it to be x squared. So this is wrong. I'm going to put it in here. I'm going to put a big X. This is wrong because g is not the derivative of f. G is the antiderivative of f. That's what makes this problem challenging. So I'm going to put it in here, a big arrow, and we're going to put the corrected. Actually, let's put it in green. The corrected version of this is that it is the derivative of g with respect to x that will give me f of x. That's what makes it challenging. You have to think, once you have f, and applying derivatives is something that is trivial to do. But once you have f, you have to think, what function g, if I were to take the derivative of g, I will obtain my function f that I'm trying to integrate. In this case, the answer will be x cubed divided by 3, because if I take the derivative of x cubed divided by 3 with respect to x, the 3 cancels and I get x squared, which is what is sitting in there. And this is what the fundamental theorem of calculus tells you. And there is usually two main ways that you can convince yourself of this. You can think of the function area, that is that function g that I'm talking about. And if you try to take a small change in that function with respect to a tiny x, it makes sense that that will tell you the height of the rectangle that you have at that moment. So basically how much the area changes from this x to this x is proportional to the height of that rectangle. So that's a way of convincing you that if you had that area function, g, small differences or small changes in that area function has to be proportional to the integrand that you have. Another way of convincing yourself of this is to think, instead of the derivative of g being in f, is if you were to integrate small changes in the derivative of a function. So if you think that g itself is some function, f is its derivative, and you're looking at the accumulation of that derivative, the total accumulation that you're going to get on the changes is going to be, at the end, the difference between the actual function that you have. So that way you can convince yourself that integrating the derivative of g, integrating the derivative of g with respect to x, this should give you g back up to a constant, which is basically integrating f will give you g. So that's another way that you can convince yourself of this. Anyways, the rest of the video, you're going to see this expression sitting there. Just know that it's wrong. I wrote the wrong thing. It has to be the opposite. I'm going to try to put a square in there that has the correct version. Hope you enjoy the rest of the video.
Well, not as simple as that, because usually finding antiderivatives is a complicated problem, not the most complicated ones that you can have, but it's complicated. But this is extremely powerful because it tells you, oh, you want to add the potato. All you have to do is find a function such that whenever you take the derivative of that function, you get whatever was inside the integral sum in there. And that gives you the power of adding the contribution of infinite objects, each one of which is infinitesimally small. That's the power of this thing. Make sense? Okay? that takes us to the final demonstration. I'm going to try to have toys in this class every time. I'm going to move the camera in a second, but part of your playground, now that I realize, I don't know if I put that in the playground directly, but part of your playgrounds is I want you to try to come up with a formula for the volume of a cylinder that looks like this. And this is my cylinder. Zoom people so you can see it. I think we can estimate this has like an inch radius. So how much is an inch? 3 centimeters of radius, height. How much is this? Like a centimeter, 2 centimeters? Yeah, let's say 2 centimeters. I will measure this later and give you centimeters correctly. What is the volume of this thing? How can you do that? Well, if somehow you were able to slice this into infinite tiny cylinders, you have to calculate the area, but you stack them all together like if this was a cake, you will get the volume. But how much is the area of each one of these cylinders? So you will have to basically calculate the area of a circle. But how do you calculate the area of a circle? Well, you can slice this up and then calculate half of the circle by breaking it up in little areas, in chunks. So you have to figure out what is the curve that describes the circle. That is 1 over 1 minus x squared. If your circle has radius 1. You will arrive at the formula that you know, pi r squared, but give it a try. Give it a try by pen and paper. You're going to give it a try by a computer code as well that I will suggest. Meanwhile, we are going to actually see how much the volume of this thing changes. So let's see if I can put this camera as well. All right. I guess that is good enough. So in here I have, I think this is called graduated cylinder, which I don't know why, because it has not graduated anywhere. And it's at 100 milliliters of water. And here I have my cylinder, and we're going to use Archimedes' principle to actually do engineering. And I'm going to ruin this thing, don't tell anybody. And this is so sad, it doesn't fit, I got the wrong one. Okay, well, I own you this demonstration because I cannot. This is so funny. This tells you that I'm a theorist. I went into the room, I saw the cylinder, and I was like, yep, this is exactly what I need, and I didn't try it. Well, okay. So, no, but this is fantastic because this gives you the chance of making a prediction. You do not know how much this is going to be. So go and do your playground, and then when we come back on Wednesday, we're going to see if you were right, and this is a volume that you said. Okay, let me go back because I have 10 more minutes that I want to show you your playground. That was anticlimactic. Okay. You have basically 2 or 3 playground homeworks for today, and I'm going to be collecting these in a week's advance because I'm going to also send you some stuff on Wednesday. So you have a week to do these things. This one, if you can, do it now. It's easier for me to then start putting more of a personal collection with you all. I send you an email with some important links. One of the links is the link to the forum. Register in the forum and introduce yourself. Josh and I are already there. You can learn about the things that we like and we do. I even have a picture of my dog. So introduce yourself in there so that I know that the forum is working and that you're able to access the things that I will put. The other two, the first one is you're going to create your own numerical derivative estimator. You have to think how you're going to do that. The name of the game, if you want to search it, is called Finite Differences, but I want basically you to be able to numerically, using Python, estimate the derivative of any curve, any function. You're going to do the same with making an integrator using Riemann sums. That basically means you have your curve, you're going to slice it into tiny rectangles, and you're going to add all the rectangles together. So write a function in Python that does that. If you have never done Python, that's completely fine. A, you can ask me for help, or B, you can see the YouTube video tutorials that I have on how to make these Python codes that are in there. Apply them both to these three cases, because these three cases, you can calculate the derivative and the integral by hand. So you can make a curve in Python, in matplotlib, that will show the actual curve, your estimate, and then the derivative, your estimate for the derivative, the integral, and your estimate for the integral. It will be very fun. Give it a try. The second part of the playground is for you to listen to this podcast. This is a podcast about the growth mindset, and it's going to be very important for the rest of your career. So give it an ear to it. It's going to talk about imposter syndrome and how, as a society, we keep screwing up by feeding everyone this myth about the lone genius and how people are into two classes. Those that are born geniuses and are able to do these type of things are those like me who are not born geniuses and then are not able to do these type of things. This will tackle why this is stupid. This will not reinforce that, because I do think that it's very stupid. So listen to that. And as a third podcast, a third playground that I forgot to add is basically the problem with the cylinder. Try to come up with a pen and paper answer to how much is the volume of a cylinder using the techniques that we discussed today. With that, we have 8 more minutes for questions and discussions if you have any. Any questions so far? Any comments? Any extra things that you would like to say? Some people. What about you? Fair enough. So those are your playgrounds. I am going to put this in the Drive folder that I guess I need to send an email with that. And next Wednesday, this Wednesday, we're going to talk about Taylor series and probably vector calculus and probably differential equations. Maybe we can cover those 3 topics in one lecture. And then lecture 3 should be linear algebra. Lecture 4 would be the other 2 things. So thank you all for coming. I will see you next Wednesday and have a fantastic rest of your day.
Thank you.
Thank you.
Thank
course.
you.